This is a review worksheet for the FU equals MA problems. Generally speaking, in these problems, what we're going to be doing is we're going to be relating the motion graphs that we were using in the CAPM units to the force diagrams that we've been using with different forces from the balanced force unit. But now, specifically, we're talking about unbalanced forces, but we're still using those same tools. And so we'll use unbalanced force diagrams in addition to the motion graphs and the FU equals MA equation kind of all together in these problems. Usually, the FU equals MA is kind of a connection between the force diagrams and the motion graphs. And so we've got some work here that's done with the forces, force diagrams, and then, as I said, it's kind of an intermediary between the force diagrams and the motion graphs. We have this FU equals MA equation, and then we can do the motion graphs. And so this is kind of how I think about it in my head. Sometimes we're given a lot of information about the motion graph stuff, in which case we'll start on the motion graphs, and then we'll use FU equals MA, and then we'll do the force diagram. Sometimes we're given a lot of information about the force diagram, the forces, and then so we'll do a force analysis on an object, and then we'll use FU equals MA, and that'll give us the acceleration, and then we'll do the motion graph stuff. So this process works either way, but the FU equals MA equation is kind of the link between the force diagrams and the motion graphs. And so, and in this case, when we say motion graphs, it's usually just the velocity versus time graph. So that's kind of the thought process that I'm going through as we go through these problems. So in this first one here, it says a 15-kilogram box is being dragged across a carpet by a rope. The box experiences a frictional force of 30 newtons and a horizontal tension force of 120 newtons. Draw an FBD for the box and then determine how far the box would travel over a period of 8 seconds, assuming the box started from rest. So in this one, it seems like it's given us a lot of information about the forces. It told us it was a 15-kilogram box. By telling us the mass, it tells us the gravitational force. So we know that we've got an Fg downward of 150 newtons. If it is sitting on a carpet or on a floor, then if it has an Fg, it also is going to have an Fn, a normal force. Okay, and in this case, it also equals 150 newtons. All right, the reason we know that this equals 150 newtons is because the box isn't going to be accelerating in the vertical direction. All right, it's not going to be moving up or down at all, actually, and so we know those two are the same. The other forces that we have here is we have a tension force, and it doesn't really give us a direction here, so if we don't give a direction, then usually the assumption is that it's going to the right. All right, so we're going to have a tension force here, and that tension force is equal to 120 newtons. And then lastly, we have a small friction force here going the other way. It tells us, all right, just resisting the motion, so FFR, and that equals 30 newtons. And so since we're able to complete this force diagram and have all the forces on it, and we know what they all are, what we can do is we can find the unbalanced force from this. Now, the unbalanced force, it's important to remember, is not a force in and of itself. The unbalanced force is kind of like what you have if you cancel out all of the forces and see what's left over. So in this diagram, the top and the bottom, 150, cancel out with each other. So those are gone. And then you look at the left and the right. Those kind of cancel out with each other to some degree, but in the end, you would still have 90 newtons of force left going to the right. So in this case, we know that Fu equals 90 newtons. The reason that's important is because then we can use the Fu equals Ma equation. All right, we know Fu equals Ma. Now we know the Fu is 90. All right, and the mass was given in the problem as 15. All right, A, and then we can solve that, and we get that acceleration is 90 over 15, so that equals 6 meters per second for our acceleration. Once you know acceleration, you can do some stuff on the motion graphs. So I'm going to go ahead and draw out what this looks like as a basic motion graph. Oh, this should be a velocity versus time. As I said, almost always we'll be using velocity versus time graphs because they're the most useful of the motion graphs. So velocity versus time. This is an object. It says assume the box is starting from rest. So it's starting from rest. It's speeding up. We're going to assume the positive direction here. And so go that way. It says it happens over the period of 8 seconds, all right, in the problem. So 8 seconds is what we've got here for our time. All right. Now, the only thing here we've got to figure out then, it says how far is the box going to travel. We want the area of this because area of a velocity versus time graph is the distance traveled. Unfortunately, we don't know the vertical side of this triangle. However, we usually call this the change in velocity, and that always equals the acceleration times time. In this case, acceleration we have found is 6, and the time we know is 8 seconds. So 6 times 8 is 48. All right, and so our change in velocity there is 48 meters per second. All right, and then to find the distance traveled, we need to find the area of that. The area of a triangle is 1/2 base times height, so distance traveled equals 1/2 times the base, which is 8, times the height, which is 48. You multiply those by each other and you get 192 meters traveled. Okay. So just to reiterate this process, what we did here, it gave us a bunch of information about the forces. We used that to find the unbalanced force. That's always the goal of looking at the force diagram. We find the unbalanced force. Then we plug that into the Fu equals ma equation. That gives us acceleration. With the acceleration, then we're able to go and build the motion graph, which is the velocity versus time graph almost always, and find how far it has traveled. Problem number 2, it says a rocket has a mass of 10,000 kilograms, assuming that rocket fuel was able to create a vertical thrust force of 400,000 newtons. How long would it take the rocket to clear the Earth's atmosphere, which has a thickness of 12 kilometers, and how fast would the rocket be going when it left the atmosphere? I tell you to ignore air resistance. So in this problem here, what we've got a rocket. It's taking off. The rocket has mass, so it has a gravitational force. It's 10,000 kilograms. All right, and so actually I'm going to draw this to a little bit of a different scale just because I know kind of how this problem is going to turn out. So if we draw this gravitational force on here, we know that the Fg is 10 times the mass, so that actually makes it 100,000 newtons. The other force we're going to have here is that thrust force. We don't have a special letter for that, so I'm going to call it an applied force. F applied. That's so, sorry, that A is horrible. F applied. And that, in this case, equals 400,000 newtons, it says. And so here's the deal. What we have to do first now is just like the last one, actually. We kind of have enough information about the forces so we know all the forces on it. There's no other forces going to be acting here. I said to ignore any air resistance. And so what we've got then is we've got an unbalanced force. You look at what doesn't cancel out here, and so there's 100,000 down and 300,000 up, and what that ends up being is a total of, 100,000 down, 400,000 up. It ends up being 300,000 up as kind of the overall net force or the unbalanced force going upward there. Then we can do the same thing that we did on that last problem where we say Fu equals ma. Okay, so if that's the case, then we know that 300,000 equals 10,000 the mass times the acceleration, right? This is Fu equals ma. Divide that there by 10,000 on both sides, and you get acceleration equals 30 meters per second. Now we have a situation here where we have a velocity versus time graph that we can make, all right, and the information that we have about it. It's starting from rest because a rocket starts on the ground, it's not moving. It takes off, it's accelerating upward in the positive direction. We know that it travels a distance of 12 kilometers because that's the thickness of the atmosphere. It goes 12 kilometers through the atmosphere. So distance traveled is 12,000 meters because 12 kilometers is 12,000 meters. Okay, so the distance traveled, 12,000 meters. We also know the acceleration is 30. Now, anytime that you know the distance traveled and you know the acceleration but you don't know anything else, what we end up doing is we end up setting this equal to t, all right, and this change in, we call this the change in velocity, which is equal to acceleration times time, which in this case equals 30t. And so what we end up with here is we know that the area here, 1/2 times t times 30t equals 12,000. Or you end up with 15t squared equals 12,000. Now if you go through and solve that, you end up getting that t equals 28.3 seconds. And then you can end up find the change in velocity here as well. Change in velocity equals 30 times 28.3. All right, you multiply that together, and you end up getting, for your final velocity, because the initial velocity is 0, you end up getting for your final velocity that your final velocity is 849. So actually this one, because it involves that whole business with the t and the 30t and you have a t squared in there, this one actually ends up being a little bit more rigorous than these typically are, but it's something good to know if you ever have a distance traveled and you have an acceleration, you need to set it up that way where one side is t and the other one is acceleration times time. Number 3 here, it says a 4-kilogram remote control car is driving down the hallway. The car travels a distance of 56 meters in 4 seconds, accelerating uniformly from rest. Assuming that there is no air resistance on the car, find the magnitude of all the forces. So this one here, it says find the magnitude of all the forces, kind of as the final question. And so that gives you a hint that we're probably going to do motion stuff first, and then find the forces in the end. Also, it tells us some things about the motion originally. It says the car travels a distance of 56 meters in 4 seconds, and it says it's accelerating uniformly from rest. And so it kind of gives a hint here, I think, based on the fact that it gives us that information about the motion and asks us about the forces, that we're going to start with the motion graph first, or the velocity versus time graph first on this one. So the things that we know here is 56 is the area here, right? And we know that it happens over 4 seconds. All right, we don't know the change in velocity here yet. But one thing we do know is that 1/2 times 4, this is the area of the triangle, 1/2 times 4 times that change in velocity has to equal the area, which is 56, the distance traveled. Go ahead and solve that for change in velocity, and you get change in velocity equals 28 meters per second. Then we can find the acceleration, which equals the change in velocity over the change in time. And that equals 28 meters per second over the course of 4 seconds, and you end up with 7 meters per second Now using Fu equals ma, because once you have the acceleration, then you can jump to Fu equals ma. That's the whole point of doing the motion graph analysis, the velocity versus time graph, is trying to get the acceleration. So Fu equals ma, Mass is 4 kilograms given in the problem. All right, times 7 for the acceleration, and we end up with the Fu equal to 28 newtons. This 28 newtons has nothing really to do with the 28 meters per second for your, or delta V. It's just kind of a coincidence that those are both 28. So no real connection there. All right, the next thing that we're going to do then is we're going to make the force diagram for this. It's a car. It's driving on the road, and so some things here. There's going to be gravitational force, Fg, and that's going to equal 40 newtons because it's 4 kilograms times 10. All right, then there's going to be a normal force as well. If you've got an object that's sitting on the ground, then it has a normal force. This is actually also going to equal 40 newtons because it's not accelerating in the vertical direction, so we know those are the same as one another. And then there's the forward force on a car. This kind of confuses people, but if you've got a car or a person walking forward, really, anything that's moving forward by kind of pushing itself forward, usually that forward push, if it's between a person and the ground, for instance, is a frictional force, all right? Or in this case, it's between the toy car and the ground. And so there's a frictional force that is going forward. And that is actually this 28 newtons that we found there. Because the unbalanced force in this case is going to be the same as the friction force because up and down are going to cancel out no matter what here, which means that unbalanced force, all of it is attributed to the friction. Friction in this case is pushing the car forward. The wheels are pushing against the ground using friction, and they're using it to propel the car forward. And so that's kind of what we end up with for our force diagram. Number 4 here says a toy wagon pulled across a floor by a girl. This one here, it says in a period of 0.5 seconds, the wagon accelerates uniformly from 1 meter per second to 2 meters per second, and then you're supposed to make an FBD and find the tension. So this one, again, hopefully if you're looking at it, you can see that I kind of give you some information about its motion first. So we're going to start with a velocity versus time graph. Things we know here, we know it started at 1 meter per second and it went up to 2. Okay, we also know that that took a period of 0.5 seconds. Okay, so what we're going to do here is try and find the acceleration from this. We care about the acceleration because then we can use the Fu equals ma equation. So some people go here and they're like, oh, I can find the distance traveled here. You could find the distance traveled, but we actually don't really care about that in this problem. We're trying to get to the forces, and the way that we get to that is by finding the acceleration, because then we can use Fu equals ma. So acceleration is change in velocity over change in time, is the slope of this velocity versus time graph. So it went from 1 meter per second to 2 meters per second, so the change in velocity is 1 over the change in time, which is 0.5 seconds it took. Okay, 1 divided by 0.5 is actually 2, and that's meters per second per second. So that's our acceleration, is 2 meters per second. The next thing we're going to do is we're going to use our Fu equals ma equation. In this case, the mass is 5. The acceleration is 2, so the Fu ends up equaling 10 newtons. All right, so we know the unbalanced force is 10. And then this kind of works out similar to the last one. We've got a gravitational force downward, Fg. It's 5 kilograms, so that's 50 newtons. All right, we also have a normal force up, Fn, which equals 50 newtons. And then I said there's a tension force here pulling the wagon forward, so Ft equals, and in this case, there's only one force that's unbalanced here because those two are going to cancel each other out. The normal and the gravitational will cancel each other out. And so we know that this unbalanced force is really attributable just to the tension. So this is going to be 10 newtons here as well. Some people on this one are confused. They think that maybe there should be a friction force acting on this. What I would say is, perhaps I could have said, assume there's no friction, but the way a wagon works is it uses wheels to try and reduce friction. And so the whole purpose of a wagon is to try and get rid of friction. And so I'm going to assume that there's no friction involved in this. It's not the same as the last one, because some people think a car has wheels and a wagon has wheels. And so why are there different situations here? Well, a car has an engine, and the engine turns the wheels, and the main point of the wheels in a car is that they're supposed to rub or push against the ground and push the car forward. A wagon doesn't work like that. A wagon has wheels, but the purpose of the wheels are to help it move freely forward. All right? And so a wagon is being pulled forward by a rope, and those wheels are supposed to not have any friction in them so that it can help the wagon move freely forward. And so wagon wheels they work quite a bit differently than car wheels do, but the whole point here is that the wagon shouldn't have friction. And so I'm not going to include friction on my force diagram. So this is kind of what we end up with here. Okay, there's going to be some more problems that come along like this, incorporating the force diagrams and the Fu equals ma equation, and also the velocity versus time graph or the other motion graphs. And so try and get a good sense of how these all work together. And if you're confused by any of this, make sure that you stop in and ask.